All right, Statics TM 210 students, thanks for tuning in. I know there's a lot going on today. Look forward to seeing you on Monday online. Couple of quick reminders. So, Quiz 4 is going to happen on Prairie Learn this Friday from 11 to 12 Central Standard Time. We'll be sending out a kind of a test version just to make sure everybody knows where to look for it. What it's going to look like. It's just going to look like a regular Prairie Learn quiz, randomized questions, except the time window is, of course, now synchronized across everyone. Quiz 4 practice problems are up on Box. Homework 4B is due this Tuesday. And then next week's homework is going to be called Homework Exam, and that's just because it's going to be the last couple of homeworks to get you ready for the final, which will be comprehensive. I'll be sending out the date for the final very soon. Just to make sure everybody knows, if you go onto the info page of our Statics webpage and you click on either discussions or office hours, you'll see now that there are links for the TAs and CAs, and each of them will hold Zoom hours. So you can just click on that link there behind the person's name for your discussion section, and you can enter a Zoom room. So TAs will be covering the worksheets. Course assistants, the CAs, during discussion time will be answering other questions. So if you have questions about the worksheet, make sure you go to the TA Zoom room. If you start asking questions about the worksheet in the CA Zoom room, then they're just going to kick you over to the TA Zoom room. And then similarly for office hours, we're going to go ahead and keep holding them as scheduled. These are all Central Standard Time slots. But again, you're welcome to go to any office hour, of course, at any time. And again, each TA and CA has their own Zoom room to help answer questions. So if you enter one and it's pretty busy, then feel free to just leave that meeting and then click on another one and see if you can get help. All right, let us know on Piazza how that's working for you so we can try and optimize that. All right, we're going to go ahead and get started on our next set of material, which is our second to the last topic for those of you in 210, and that's internal forces. So we've already started to look at this when we were looking at truss systems and looking at whether or not the members were in tension or compression. But now we're going to apply this more broadly to any structural member. It really could be anything. It doesn't have to be something structural engineering related. But internal forces are the ones that tell us what the actual loading conditions are. And so it's possible that we have objects that have more than tension and compression, but could also have alternative loadings. So let's make sure we're on the same page. So to recap, we start first with external forces and moments. So these are the ones applied by something externally. And we've now gone through the process of identifying what are the constraints that keep these objects in equilibrium. And so here, when we have a free body diagram without the constraints drawn in, then we need to include those constraint reaction forces. So on the roller, we just have a vertical one, and at the pin, we have a vertical and a horizontal force. Now, just like method of sections, we can take one of these and split it apart and actually look and see what are the loads. Load being our generic term for forces and moments that might be acting, again, inside, right? And so we know that materials build up stresses. And if I take this left-hand side, so I've made this blue section, I'm drawing the left-hand side. This is essentially exactly like a fixed constraint. This thing is not allowed to stretch in the horizontal direction. It's not allowed to shift up and down, and it's not allowed to bend. And that means that there are internal forces that are resisting these external and constraint loads. And so these are the internal loads that we're talking about. And they're going to be called a normal force, which is perpendicular to the face that I've cut. A shear force, which is kind of like a sliding force, which is parallel to the face. So the face here is this part, right? So I can draw it like that. So you can see that the N is perpendicular to that, whereas the V, the shear, is considered in parallel. And then we have a possible moment, right? And that's what that one is going to be called. And all of these are the internal forces. So these are internal forces and moments. Now I can also draw them on the other side, and of course they have to be equal and opposite to the ones to each other, right? Since this object is in equilibrium. So if I draw the other side of this beam, and I still have all of the external loads that were applied, and I have my constraint load on the right-hand side, inside the material on that face, there's going to be a normal force this way, a shear force, V is shear, and then a bending moment this way. And so these are also internal forces and moments on the right-hand side. Now, why do we care about this? Mostly because we want to make sure that the material, the object, whatever it is going to be able to sustain the external load. So if N, M, or V get too high, then of course it's possible that things will break. And so here's an example, yet another bio example where this is a hip replacement, it's that top part of your leg. This is an x-ray, and you can see, hopefully, right, that we have this stem that is not supposed to do that, right? So we've got this break. And in this case, you can see it's kind of a shift right and left. The stem should be, like this, but of course it's now shifted over. And probably due to shear forces, right, that are kind of creating that in this case, sideways shift. So we want to be able to calculate what the internal loadings are in any of the members that we care about in order to make sure that they are in fact strong enough for the applied loads that are expected. So let's start first with a little bit of sign conventions. So, Our sign convention that we're going to talk about is actually a little bit confusing, only in the sense that we're going to call these loads positive, a positive normal or shear force. So normal, again, is the one that has the N. I don't know why that does that, but and again, it's preventing perpendicular motion. And so the convention that we're going to use is that we're going to assume that positive normal forces are tensile forces. And now that is not to say, right, let me draw these. So here's our positive normal force on the left-hand side, a positive normal force on the right-hand side. But notice that in a global coordinate system, this one still has a negative sign associated with it, right? This is in the negative x direction, but it is considered a positive, quote unquote, normal force because it's acting in tension. And then, of course, the one on the right is already positive because it's pointing in the positive x direction, right? So that's our convention for positive normal forces, and they again prevent perpendicular motion. Again, if we consider the face here, we see that that N is actually perpendicular to the face that we've sectioned. Now we can also look at the shear. So in the case of positive shear, then we'll draw our section cut. And now shear prevents, like I said, parallel to the face motion. So the convention for positive shear is that it's going to be sort of in the direction that creates clockwise movement. So this will be V here and here. And if you imagine, if you follow this arrow on the left around, it's going to rotate this way. And this one is going to rotate this way around the beam. And so both of those are in the clockwise motion direction. And that's just the convention that we'll use for positive shear. The last one is going to be a moment, and in this case, they generate concave bending moments. So a positive moment is going to be one that generates concave bending, or you can think of it as a happy moment. So what does that look like? That means we apply a moment this way, and if I drew a little face in here, then I have a happy face. And so if I want that same happy face on the right-hand side, then I have to draw, again, a moment going this way, right? So a moment that goes like this, right, on the left, countering that would actually be a frowny face moment. So let me just clarify that. So this, right, would be a frowny face, which is not correct, right? So anyway. Just stick with this for now. All right. So our sign convention, therefore, is for positive normal forces, N. They act in tension. Positive shear forces, V, are going to generate, again, that sort of clockwise motion. And then our positive moments, M, result in concave bending or a happy moment.